What was the geodesic equation for a flat space or a flat coordinate system and so on? It was simply either mx plus b or in space-time, x double dot is 0, or I'm using r double dot is 0. That's the straightest line. That's the geodesic equation for simplest flat space, flat coordinates, whatever. Right? I'm not using the theta phi coordinates, just the r coordinate. R double dot is equal to 0 is the definition of a straight line. Straight line equation, geodesic.
Right.
What is the connection on space-time?
What is the connection?
This is the equation of the geodesic when there's more complicated stuff happening. There's a correction factor.
Okay.
Okay? What is the connection on space-time? What is we have a TR, right? There's a space-time connection. There's free fall world lines, gravity, the acceleration, the world line curvature. What's the world line curvature? Gm over r squared. So this is Gm over r squared for space-time.
Space time or space plus time?
Right, space plus time. For space plus time, it's Gm over r squared. Okay? So basically I have r double dot plus Gm over r squared equals 0. That's going to be my geodesic equation.
Okay.
That's going to give me the straightest possible lines. Not r double dot equals 0, which we would have thought in the age when we thought that there was such a thing as inertia, which was straight space-time lines. We now know that free fall world lines are the straightest possible lines. They're the geodesics. They give the structure that we call the connection to space plus time. And that equation is r double dot plus Gm over r squared equals 0. Now what is that equation? Have we ever seen such an equation? R double dot plus Gm over r squared equals 0? Of course we have. That's the equation of gravity.
Right.
The acceleration of gravity is equal to
Negative.
minus Gm over r squared. So in other words, this equation that we always took as the equation of just gravity is really the geodesic equation. Correct?
Okay.
All right? Instead of saying that you have forces, accelerations, and stuff like that, we now see this equation. R double dot plus Gm over r squared equals 0. So this is simply a gravity equation. But we've put in a lot of stuff here. We put in the equivalence principle. We define the world line curvature in a naive TR. What we can do in Newtonian physics, we can just nothing. Define the calculus curvature, call it gamma. We write it now like this. R double dot. And this is minus because it's attractive. Okay, so we have a minus, this becomes here plus R double dot. In ordinary Newtonian physics, I could write this equation in this new theory that's stimulated by seeing it this way becomes some kind of a curved space-time equation. Okay? What does this say in the context of a curved space-time equation? This is simply that geodesic equation that we saw. This is a geodesic equation for R. Instead of R double dot equals 0 as the equation of the straightest line, which it would be in ordinary space-time. Right? We're now seeing this equation, which is simply the gravity equation. Since we're interpreting it within the context of a curved space-time, right, which we clued in by this, we saw the curvature of the world line, which is, could be a Newtonian diagram too, but we're interpreting it because there's no m here as a curvature of a space-time. So we're taking this equation now and saying, looking at it with new eyes and saying, okay, this is a space-time curvature equation. We now can interpret this as a geodesic equation in that curved space-time. Right? It has exactly that form that we spoke about before. The second derivative of the thing plus something else. What's this thing over here? This is gamma. GM over R squared. But overall, you can kind of see here, this is a geodesic equation. So that's the progression. We start out putting an equivalence principle into ordinary Newtonian dynamics. We define the world line curvature in a naive TR because of the disappearance of M inertial and then gravitational canceling each other, so that this is a function only of space or space-time. At any point in space-time, you can define GM over R squared. We can define it as curvature, and instead of saying the world line is curved, we can make the space-time curved, taking up the world line curvature, making the world line straight. So instead of a curved world line in a flat space, we warp the space-time so that the world line curvature becomes a straight line. Now we're reinterpreting the world line curvature as the connection curvature of a curved spacetime. All right? And that's exactly the form of the geodesic equation we saw, except that here we expected to find terms in something dx, dr dt, or dr d something over here equals 0. And there's a good reason why that's not here. I totally reinterpret this equation now. I say, I'm going to interpret it now that there's a curved spacetime. And the spacetime has a Riemannian curvature and a connection curvature. And the connection curvature is going to be given by this. Really, it's not exactly going to be like this because I have a more sophisticated theory, but where gravity really works, I'm going to expect that it's going to be very, very close to this. Okay? And I'm interpreting this equation now, the same equation, as a geodesic equation, which I couldn't do in Newtonian gravity. This wouldn't make sense as a geodesic equation. The geodesic equation is R double dot 0. But if I have a curved space-time, then my straightest line, like when you had here, the straightest line, like in curved coordinates, curvilinear coordinates, the straightest line equation can have other terms, like we had this theta double dot plus gamma theta dot or something like that, right? So the straightest line equation is going to have something like this. Basically R double dot plus GM over R squared. So this is a geodesic equation. All right? So when you look at this equation, now just look at R double dot equals GM over R squared. With all that, now you can look at this and see this as the geodesic equation for R of the straightest line in a curved spacetime. Or Newton's law, same thing. And you expect that it'll give you the same results because Newton's law works. Or where it works very well, we'll expect that it'll give us something very much like this. There'll be other terms, but like I said, the special relativity will knock it down for low speeds. And maybe there's a term that has to do with a very strong field. So near the sun it won't work. But near the Earth, for the kind of speeds that we're used to for Newton's theory, we'll expect that the equation that we get for a rigorous four-dimensional space-time curvature theory with, will give us this. All right?